Good afternoon, everybody. My name is Giovanna Calvín. I am a PhD student, and it's a pleasure to be here to talk about our last research entitled A Numerical Method for Obtaining Plasticity-Induced Crack Closure. This work was carried out together with researchers Mikel, Escalero and Haritz Zabala from the Ikerlan Technology Center and Professor Miguel Muñiz-Calvente from the University of Oviedo. The outline of the presentation is the following. Firstly, I will introduce the study, defining the industrial context, the literature review, and the main objective. After that, I will describe the developed work, starting with the definition of the case study, material, geometry, loads. After that, I will describe the method to obtain the crack closure distribution through the thickness based on the crack tip opening displacement. Moreover, I will show the results and its applicability limitations. After that, we try to solve these limitations, describing a new method. In the third section, I will show the results obtained with both methods. And finally, I will summarize the most relevant conclusion of this work, and I will comment the future task. So, under certain conditions of work, it's normal that material or manufacturing defects evolve into cracks. During these fatigue processes, the crack propagation through material causes a gradual loss of the structural carrying capacity until the final failure. For this reason, it's very important to make realistic predictions of fatigue crack growth. The most relevant conclusions derived from the literature review are, first, the fatigue crack growth depends on the loads and the plasticity-induced crack closure, or PIC. This PIC is the most relevant plastic phenomenon that reduces the crack growth velocity due to the contact between the crack faces. Moreover, different literature models for obtaining this PIC are dependent on the stress ratio. However, there is not a unique valid model for each of them. And finally, despite the improvement of numerical techniques, reproducing the real crack growth by 3D simulations, it is still a great challenge. So, the aim of this work is to develop a procedure for obtaining the 3D numerical crack closure for any stress ratio. Well, the S275 steel was chosen for this study due to its widely employed steel in the industry, due to its good properties such as weldability or malleability. Moreover, it has a low gel strength, which promotes the plasticity effects, such as the PIC. The geometry selected for this study was a compact tension specimen with a thickness equal to 2.4 millimeters and one normalized crack size. Moreover, this geometry was subjected under constant amplitude loading, varying the stress ratio from -1 to 0.6. Focusing on the numerical results, to reduce the computational cost, a quarter of the specimen was simulated in ANSYS. Moreover, to capture the effect of the PIC, the mesh was divided in three main regions. First, the propagation zone, that was composed by the smallest elements. Moreover, the local mesh that allowed a soft transition between the propagation zone and the global mesh, and the rest of the mesh was the global mesh. In addition, the elastoplastic parameters were introduced according to the Chabot kinematic model. A straight crack front shape was used in this study because we have been demonstrated in a previous work of the authors that considering the real crack front shape did not improve the crack closure results. And finally, here you can see the crack growth scheme, which is composed by one unload cycle, 20 load debound unload cycles, considering the node releases for the crack propagation, and 8 cycles to stabilize the material response. And finally, the same load increment was used to measure the POP max or crack closure. So to address the analysis of the crack closure distribution to the thickness for any stress ratio, the crack tip opening displacement method was used. This method is based on monitoring the displacement of the first node behind the crack front to identify the opening load when the node displacement is positive. Here, in these figures, you can see how the POP max is obtained from the C2D versus load graph for the cases and the midplane node and the surface node. Moreover, you can see that here, the midplane node is always open, while the surface node starts to move from a certain or opening load, this here. So, repeating this procedure for the rest of the crack of the following, well, along the thickness, the crack closure distributions through a thickness can be obtained as follows. Moreover, here you see that the most of nodes are already open under the minimum load here and has a constant value and equal to the stress ratio. However, the surface nodes here are progressively opening, which indicates that the crack closure was located here, close to the surface. So, moving with the results, on the one hand, for positive stress ratios, similar trends were identified. First, the crack was open for a great part of the thickness close to the midplane, this here. Moreover, the values between the midplane and the surface decreased with the decrement of the stress ratio. The crack closure was located on the surface here, and the surface values were higher than the midplane values, according to the previous work. On the other hand, focusing on the negative stress ratios, similar trends to those obtaining for positive stress ratios were identified. However, the results for the midplane indicate that the crack was open despite the significant compressive load here. So the question was, did this fact make any sense? Let's try to answer it. Here, you can see the contact element pressures from the beginning to the end of the crack propagation. Here. There was a non-contactic area that, close to the final crack, that was caused by the excessive element deformation behind the crack tip here. So it can be stated that the crack closure obtained based on the C2D for negative stress ratios was not suitable for this case. So at this point, the following problem appeared. If the most used method did not work properly to obtain the crack closure distribution under negative stress ratios, how could we calculate it? Well, to solve this problem, we propose a new method based on 5 steps. The first step was the definition of the finite element model, then the simulation of the crack growth. In the third step, the calculation of the contact element pressures. In the fourth step, the calculation of the average of contact element pressures for each column. Yeah. And finally, in the 5th step, the determination of the opening load. Here, in the figures below, you can see that, again, 2 examples for a midplane element, midplane column here, and the surface elements. Moreover, you can see here that the element pressures located on the surface elements was higher than the midplane column elements. And it's due to the crack size of the plastic, the size of the plastic wake generated during the crack propagation. So again, reproducing this procedure for all columns through a thickness, we have here the peak distribution through a thickness. So following again with the results, focusing on the positive stress ratios, same trends as those obtained with the CTO method was identified. However, in this case, the mid-plane values were close to the 0, indicating that the crack started to open from a tensile loads. Well, to assist the suitability of this new procedure, the results obtained with both methods were compared. Focusing on the negative stress ratios, we see that the values were overlapped toward the surface, here and here. And departing from the midplane, the values shows a large variation, reaching differences of more than 100% here. And finally, turning to the positive stress ratios, the peak distribution through a thickness was similar for the both methods, and it can be stated that the new method was validated. So, summing up the main conclusion of this work, it was found an uncertainty of using the vertical displacement of the nodes, well, of the first node behind the crack tip, to obtain the crack closure distribution through a thickness under negative stress ratios. So, to solve this problem, a new method to obtain this numerical crack closure for any stress ratio was developed and validated. And to end the presentation, in future tasks, we will analyze the influence of the crack size on the crack closure calculation by the new method. So that's all. Thank you for your attention, and I hope you found it interesting work.